Hey guys, welcome to lecture 4. Today we're going to start by talking about the fundamental theorem of calculus. Then we're going to introduce integration. And then we're going to finish off by talking about Riemann sums. Let's start with this. So we have this note over here at the top that says, let big F of x be the antiderivative of the function little f of x equals x, which means big F prime of x equals x. And suppose that Kyle knows that big F of 0 equals 1, but that he doesn't know what function big F of x is. Without knowing what big F of x is, how could he approximate the value of big F of 3? Okay, now we know what big F of x is, right? Last time we developed some techniques to come up with the antiderivatives of polynomials. So we know that big F of x is this function here, which is x squared over 2. And then that plus 1 comes from the fact that we know that big F of 0 is 1. We could draw all of these tangent lines to big F of x, and a different tangent line over every 1/2 interval. In this case, that's just 1/2 interval is just a number that we're choosing right now. And would Kyle be able to draw these tangent lines? Well, Kyle knows that big F of 0 is 1. So Kyle knows that this point is on the graph. The point 0, 1 is on the graph. And he knows big F prime of 0 because that's the same as little f of 0, which is 0. So he knows that the slope at 0 is 0. So he's able to draw this point, and he's able to draw this whole tangent line because he knows that there's a line with a slope of 0 tangent to this point. What about this next tangent line here? Is Kyle able to draw this tangent line? Well, Kyle knows that the derivative at 0.5 is 0.5, right? We're just plugging 0.5 into the function f of x equals x. So he knows the slope of it, but he doesn't know this point. He doesn't know the point 0.5, 1.125. So he's not able to draw the line through that point. He only knows the slope of the line, but he doesn't have a place to connect it to. So his best guess here is to just use this first tangent line as an approximation for the function. And then instead of drawing it tangent to the graph, to draw this tangent line just connected to that past tangent line that we drew there. And the same thing for all these next tangent lines. He knows the slope, but not where they touch the graph. So we're just going to connect all of these down to the past tangent line. And then we have this sort of approximation of our graph, right? And we're using these 1/2 intervals. And so we have a different line segment at every 1/2 interval. And using this approximation that we constructed, we have a guess that big F of 3, right, is about 4.75. And how close is that? Well, we see that actually our big F of 3 is 5.5. So we were a little bit off. We were off by 3/4. Now, what if instead of intervals of length 1/2, we used intervals of length 1/4? Well, then we could use these to construct an approximation of our function in the same way. And if we compare this construction with the construction that we got from intervals of length 1/2, we find that this 1/4 construction is an even better approximation of our function. And this should make sense. If we think about it, would we draw our real function? Our tangent line is being updated continuously. When we use an interval of length 1/2, we're updating our tangent line every 1/2. When we use these intervals of length 1/4, we're updating our tangent line every 1/4. And so we're getting closer and closer to this continuous updating of our tangent line. And so as our intervals get smaller and smaller, our approximation gets closer and closer to our function. So now let's try a similar example by hand. We're going to suppose that big F of x is the antiderivative of little f of x equals x squared. We want to figure out how much does big F of x increase between x equals 1 and x equals 5. And we want to approximate using step size 2. Notice that we're not given what f of 1 is, what big F of 1 is. So we're just going to draw on our graph over here some number that we're going to call c. And so we'll put a point there. And we're just trying to figure out how much it increases. We're not trying to compute the value. And we can't compute the value because we have no initial data for our function big F. Now, just a quick reminder, that since rise over run is our slope, then we can say that rise equals slope times run. And that just comes from multiplying both sides by run. Now, approximating our big F by line segments, we're going to have to find the slope at all of the points that begin our line segment. So at 1, we have n equals big F prime of 1, which is our little f of 1, which is 1 squared. And so that's 1. So our slope is 1. And so since we want to go over by 2, right, we're approximating with step size 2. So we're going to go over by 2. So how much are we going to go up? Well, our rise then is going to be n times run. So that is going to be 1 times 2, which is 2. Okay, so we're going to go up 2, and I'm just going to call this point c plus 2, since we know that this distance between them is 2. And so we'll go up by 2, and we'll connect those by a line. Now we need to do the same thing starting at the endpoint of this first line segment. And so that is x equals 3. So we're going to go here, and we're going to say n equals f prime of 3, which is little f of 3, which is 3 squared, which is 9. And so what does that mean? Well, that means that our rise over our next interval is going to be n times run, which is going to be 9 times 2, which is 18. So we're going to go over 2, and then we're going to go up 18, and we can kind of just label our scale however we want. So I'll just go up about to the top of this graph here, and then we'll draw a line between these 2 points. And we said that we went up by 18, so we'll say that this distance is 18, which means that we have to go c plus 2 plus 18. So this point here is going to be c plus 20. And so our guess is that we increased by 20 between x equals 1 and x equals 5. And I think that's pretty clear to see from our drawing, but if you did want to see that a little bit more formally, right, the distance between 2 numbers we can find by subtracting them. So we could say c plus 20, that's our top number, minus c, that's our bottom number, right? And of course, these c's are just going to cancel out, so that gives us 20. But now let's look at what the actual answer should have been. So remember, we do know how to find the actual antiderivative of a power function using our reverse power rule. And since our derivative is x squared, then our original function must be 1/3 x cubed plus c, right? We don't know what that c might be because any derivative of this, regardless of c, is going to be x squared. Then let's find f of 1. So f of 1 equals 1/3 times 1 cubed plus c, which is 1/3 times 1 plus c. Okay, so that's 1/3 plus c. And then let's find f of 5. Big F of 5 is 1/3 times 5 cubed plus c. So that's 1/3 times 125 plus c, which we can only rewrite as 125 thirds plus c. And so this difference, f of 5 minus f of 1, equals 125 thirds plus c minus 1/3 plus c. And so that's going to give us, let's actually just distribute. We're going to get 125 thirds plus c minus 1/3 minus c. And notice that these c's cancel out. So that's actually a somewhat important fact about this, is that the amount of change in this antiderivative function is independent of c. So whatever that c is doesn't matter in terms of the amount that a function increases between one point and another. And so then we can just subtract these constants here. And so we're going to get 124 thirds. And we find that that is equal to 41.3 repeating. So that's the real answer. And our guess was 20. So this is really, really off. And why is it so off? Well, it's going to be so off because we used this huge step size of 2. Remember that in our Desmos graph, we used a step size of 1/2, and then we saw that it was more accurate using a step size of 1/4, and we could keep shrinking it and making it better and better. The step size of 2 is really big, and so
our answer is potentially going to be really off. And in here we see that the real answer is more than twice the answer that we guessed. But now let's reflect on how exactly we found this approximate increase. Notice that we said over this first interval, we increased by 2 times little f of 1, and then we said plus 2 times little f of 3, right? That was our 2 times 1, and then for that second increase, it was our 2 times 9. And now we're going to draw a graph of our little f function. So our little f function, we said was x squared. And so let's just kind of sketch what a parabola looks like. And we're going to draw our 0, 1, 2, 3, 4, 5. And now let's draw rectangles underneath of this graph that touch the graph at the top left corner. And we're going to start those rectangles at 1. And we're going to make all those rectangles have width 2. And we're going to start another one at 3. So I'm using the same starting points. And now let's think about how I would calculate the area of these rectangles. So for this first rectangle, we're going to say that the area is length times height. And so that's 2 times, well, now what's the height of it? Well, the height of it is this side over here. The height of it is exactly going to be little f of 1, right? This is our little f function. Okay, what about the second rectangle? Well, the area is again length times height. Our length of that is 2. And how tall is it? Well, the height is right here. And so that height, again, is little f of 3. So what's the total area of these rectangles? That's going to be 2 times f of 1 plus 2 times f of 3. And notice that that's exactly the same calculation we did up here. So there's this sort of coincidence that the area of these rectangles underneath of our derivative graph is exactly the same as the amount that our approximation increases. Now, let's think about what would happen if I made smaller rectangles. What if I made a rectangle at every half instead of every 2? So starting at 1, we'd go and we'd make a little rectangle like this. And we're repeating that at every multiple of a half between 1 and 5. And look at the difference between these two pictures. If we think about this total area underneath of the graph between 1 and 5, which one of these total areas of the rectangles is going to be closest to the total area under the graph? Now, by total area under the graph between 1 and 5, I mean this area in here. And we see that as we add more and more rectangles, we fill in more and more of that area. Let's look at that once again. We see that with these large step sizes, there's a lot of missing area, right? All of this area up here is not included in the total area of those rectangles. But when we use smaller rectangles, there's a lot less area that goes unaccounted for. And so it should make sense that as we use more and more rectangles, the sum of the area of those rectangles approaches the actual area underneath of the curve. So we see that using a smaller step size makes the rectangles better approximate the area under the curve. We also saw that the sum of the areas of the rectangles was the same as the change in our antiderivative function approximated by line segments. So we have this relationship that the sum of the rectangles, as the step size gets smaller, is going to approach the area under the curve. And the change in the antiderivative function, when approximated with line segments, as the step size gets smaller, is going to approach the actual change in the antiderivative. But we saw that these two things are equal, which means that I could just change their place in this diagram, and this relationship would still be true. And so what that means is that I can actually draw this same arrow right here and say that as the step size gets smaller, the sum of the areas of the rectangles is going to approach the actual change in the antiderivative. But we also know that it approaches the area under the curve. And so the two things it approaches have to be the same thing, which means that these two things are also equal. And that is a very important fact. And in fact, it is such an important fact that we give it a very important name. That fact is the fundamental theorem of calculus. In particular, it is the second part of the fundamental theorem of calculus, which is also called the net change theorem. But before we write a concise definition of the net change theorem, we want to define integration. Now, integration is defined as the process of taking an integral. So we're going to define an integral by saying that the integral from a to b of f of x is the area under the curve of f of x between x equals a and x equals b. And we could try to draw a little picture of this. We'll call this curve f of x, and we'll mark some points a and b on our axis. And then we're saying that this area here is the integral from a to b of f of x. Now there's a shorthand notation for this phrase integral from a to b of f of x, and that is this. We say the integral from a to b to x is written as this symbol right here is the integral symbol from a to b of f of x, and then at the end we write dx. And that says that the x is our variable of integration, basically that we're integrating along the x-axis. So if instead of an x-axis we had a t-axis, then that would say dt. Or if we wanted to integrate with respect to y instead of with respect to x, that would be dy. And that's actually somewhat common. Actually, dt and dy you'll see a lot, but you could just replace that variable with any letter at all, as long as you replace the letter in your function. And that would mean exactly the same thing. But conceptually, for example, if you have some function that is defined in terms of y, and so you have a function like this is your y-axis, this is your x-axis, and you had y values of c and d, and you wanted to find the area between the curve and the y-axis, so this area here, that could be written as the integral from c to d. And let's give this function a name. In terms of y, we'll call it g of y. So this is the integral of g of y dy. Now a quick note on our notation. This part is called the integral symbol. These numbers that we have on the top and bottom are called the limits. Now this is the same word that we use when we take a limit like we did in the past. Like, for example, the limit as n approaches infinity of 1 over n equals 0. But it's just the same word, and these are essentially unrelated ideas. The function that we have in the integral is called the integrand, and the variable at the end is often called the dummy variable. This is because the result of this integral does not depend on what letter we use here. We could replace it with any letter and we'd end up with the same number. And this entire part, the dx, is sometimes called the differential. We remember before that when we were calculating the rectangles underneath of a curve, we were multiplying the width of the rectangle by the height of the rectangle, and then we were adding them together. So in some sense, we had our f of x, which was the height of our rectangles. We multiplied that by the width of our rectangles, and then we added all of those together. Now, the way that Leibniz thought of integrals was essentially as these really, really tiny rectangles that are so small that they're just a line. And the width of that rectangle is what he calls dx, which is this really, really tiny, tiny width, what he calls an infinitesimal width. And so he takes that width and he multiplies it by the height, and we know that the height is f of x, and then he takes all of those and he adds them together. And so he's saying the sum, and for the sum, he writes this weird S symbol. And if you've ever read a really old text, you might know that these really old-fashioned S's sometimes were written in this way. So it's the sum of the height times the width of these rectangles, and we add them all up and we get the area under the curve. And so that's actually the origin of this notation. Now let's do a couple examples. So let's find the integral from 1 to 3 of 2 with respect to x. All right, so let's draw a quick sketch of this. And so it's just the function 2. And so that looks like this. And we're going from 1 to 3. And so that means that we want the area under this graph of the line y equals 2 between 1 and 3. So the area equals our length times our height. And so the length is 2, and the height is 2. And so the area is 4. We're going to say, so that is going to be 4. Okay, let's try another example. Let's find the integral from 0 to 4 of x dx. All right, let's do a sketch of this. So x is a line, and we're finding the area between 0 and 4. So that's this whole area here. And let's label some lengths here. So this is a distance of 4. Since it's just y equals x, then when x equals 4, y is going to be 4. And so that means that this height here is 4. Now this is a triangle. And so we know that for a triangle, the area is 1/2 base times height. And so we're going to use 1/2 times 4 times 4. So that gives us 2 times 4. So that gives us 8. So this is going to equal 8. Let's try another one. Let's go the integral from 1 to 4 of 2x plus 2. Okay, let's graph this. And so 2x plus 2, so we're going to have a y-intercept of 2, and then we're going to have a slope of 2. And we can just adjust our scale so that that is a slope of 2. And so we'll go 1, 2, 3, 4. 2 times 4 plus 2 is 8 plus 2. That's 10. So that means that at 4, we're going to be at 10. Now when we plug in 1, we're going to get 2 times 1 plus 2. So that's 2 plus 2, which is 4. And this is the distance between 10 and 4. So that's 10 minus 4, which is 6. And this height is going to be 4. And then we see that this is the distance between 4 and 1. So that's going to be 3. And what we want is this entire area, right? It's the area under this curve between 1 and 4. So if we think about just the area of this triangle here, then the area is going to be 1/2 base times height. That's going to be 1/2 times the base is 3 times the height, which is 6. And so that's going to give us 1/2 times 18, which is 9. And then down in this rectangle, we have the area is length times height, which is 3 times 6, which is 18. And so the total area is going to be 9 plus 18, which is 27. Okay, let's do another example. Let's go the integral from -2 to 2 of the square root of 4 minus x squared dx. Okay, what does this graph look like? This is a type of function that you do need to be able to recognize. And if you're having trouble knowing how to graph that, let's take a look at something off to the side. And let's look at the graph x squared plus y squared equals 4. And then we're going to subtract x squared from both sides to get y squared equals 4 minus x squared. So y equals plus or minus the square root of 4 minus x squared. Now, what does the graph of this original thing look like? That's something that you should definitely be able to identify. That's going to be a circle of radius 2, right? Because a circle has the form x minus h squared plus y minus k squared equals r squared, where h comma k are the coordinates of the center of the circle. So in this case, our h and k are both 0, and our radius is 2, because 2 squared is 4. So we're centered at 0, we're a circle of radius 2, so it looks like this, which means that this last equation looks like the same thing. But since in our integral, we don't have this plus or minus, we just have the plus part. That means that we're going to take the bottom part away. And so y equals just the positive 4 minus x squared is going to look like a semicircle from -2 to 2. And if we want to take the integral of this, we're saying the area under this curve from -2 to 2. And what's that going to be? Well, what's the area of this circle? Well, area equals pi r squared. So it equals pi times 2 squared. That's going to be 4 pi. But the area of this is going to be 1/2 times my 4 pi, because that's a half of the area of the full circle. So that's going to be 2 pi. And so we have that the area under this curve, which is this integral, is going to equal 2 pi. Now that we have a good sense of what integrals are, we're ready to concisely define the net change theorem. We noted before that the area under the derivative function from a to b is exactly the same as the amount that our original function changes between a and b. And so now we can write that like this, that the integral from a to b of f prime of x dx equals f of b minus f of a. And that is the entire statement of the net change theorem. Now, what if we have a function whose derivative is negative? For example, we could say let big F of x be the antiderivative of little f of x equals -2x. We know that that means that big F of x equals -x squared. So let's just write that. So big F of x equals -x squared. And if we graph that, we know that we have a function that's decreasing like this. So let's plot a couple points. Let's say 1, 3. So this point is going to be 1, -1. And this point is going to be 3, -9. So how much does this function change between 1 and 3? Well, it goes down by 8, right? And formally, we could write that as f of 3 minus f of 1, right? Big F here. And so that's going to be -9 minus -1. And so that's -9 plus 1, which is -8. And so based on what we're saying above, that means that we should be interpreting the area under our derivative function as -8. Well, let's take a look at the graph of our derivative function. Well, that's -2x. And we're looking at this area between 1 and 3. And so that's this area here. Now, what does it mean for an area to be negative, right? Because typically area is a quantity that's always positive. Well, in order for this model to be consistent, when we have a negative value of the function, that's going to mean that our area is below the axis. And so we're going to say that any area below our x-axis is a negative area. So we're going to define this area as negative because it's below the axis. And that's in order for this model to be consistent. Because as we saw, this area must be -8. So now let's say that big F of x is the antiderivative of little f of x. Big G of x is the antiderivative of little g of x. And big H of x is the sum of big F and big G. We want to see how much does big H of x change from a to b. So H of b minus H of a. So what does that mean? Well, H of b means f of b plus g of b. And then we're subtracting h of a, which means f of a plus g of a. So let's distribute here. And then let us rearrange a little bit. So I'm going to put these f's together and these g's together. So we have f of b minus f of a plus g of b minus g of a. Okay, so what did we just do? It maybe doesn't look that interesting, right? But this first part here, we're saying how much does f plus g change between a and b? And so this, by the net change theorem, is the integral from a to b of little f of x plus little g of x dx. And this, by the net change theorem, is the integral from a to b of little f of x dx, while this is the integral from a to b of little g of x dx. And so what did we just show? We just revealed a property of integration, which is true in general because we just showed it for general functions and general endpoints. And that says that the integral from a to b f of x plus g of x dx equals the integral from a to b of f of x dx plus the integral from a to b of g of x dx, which is exactly what we just wrote above. Notice also that if we made f and g the same function, for example, I could say, well, what is the integral from a to b of 2 times f of x dx? Well, that's the integral from a to b of f of x plus f of x dx. And so by this property that we just showed, that's the integral from a to b of f of x dx plus the integral from a to b of f of x dx. And so that is going to be 2 times the integral from a to b of f of x dx. Right. And we could do that again, right? I could put a 3 in front of there and then break it apart into 3 functions. And so in general, we have this property that says the integral from a to b of some c times f of x dx equals c times the integral from a to b of f of x dx. Now that we have these, let's do a couple more examples. What is the integral from -3 to 3 of 2 times the square root of 9 minus x squared plus 2x plus 4 dx? Well, if I just tried to graph this, it would probably be difficult to graph this function to begin with. Not impossible, right? We could do all the tricks that we did a couple lectures ago where we find the inflection points and all that. But then even after we graphed it, we'd have trouble identifying the shapes, right? It wouldn't be these geometric shapes that we know how to graph. But we can use this linearity property to break this into separate integrals that do have identifiable shapes. So let's try that. So that's going to be the integral from -3 to 3. And I'm going to use just this first part here. So I can pull a 2 out in front like we saw. And then I can just write what's inside. So 9 minus x squared dx plus, and I could pull this 2 out in front if I wanted, or I could leave it inside. It's not really going to matter. And then same with this last one. So now we have all of these 3 different integrals, and all of these integrals are going to represent a shape that we do know the area of. So for this first one, just like before, hopefully now you can identify this, that this is going to be a semicircle of radius 3, and we're integrating from -3 to 3. So it's this semicircle, right? And so the area of a circle is pi r squared. So the area of a circle would be pi times 3 squared, but this is only half of a circle, so we have to put a 1/2 in front of it. So that's going to be 1/2 times 9 pi, or 9/2 pi. And so that's this part is 9/2 pi. And then we're multiplying by a 2. So overall, that first part gives us 9 pi. Okay, integral from -3 to 3 of 2x. Let's see what that looks like. So -3, 3, and then we have the line y equals 2x. And so this is going to give us -6, and this is going to give us 6. And so each of these triangles has an area 1/2 base times height, which is going to be 1/2 times 3 times 6, and that's going to give us 9. So this triangle has an area of 9, but this other triangle is below the axis, and so we're going to say that that has an area of -9. And so altogether, that just has an area of 0. So we're going to say 0 here. And then we've got this one last one to look at. So the integral from -3 to 3 of the function y equals 4. So that's just going to give us this rectangle. And so the base of that is going to be 6. And the height of that is going to be 4. And so area is length times height, which is 6 times 4, which is 24. So overall, we get an area of 24 plus 9 pi. Let's look at something else. So notice that the integral from a to b of little f of x dx, and we'll just use this same general f of x that we're talking about up here, which has antiderivative big F. So by the net change theorem, that equals f of b minus f of a. And now I want you to notice that that's the same as if I said negative outside, and then I also distributed a negative through this. Right, so these two negatives are going to cancel. So take a second to look at that. Right, if I were to distribute this, this first f of b would just be positive f of b, and then the second f of a would become negative, and so we get what we started with. So these are equivalent. And then inside here, I'm going to switch the order of those, and so that's fine to do. Okay. And now if we think about what this says inside, right, the big F of A minus big F of B, well, the thing that comes first was our upper bound, and the thing that came second was our lower bound in our integral by the net change theorem, and now we have a negative out in front. Okay. And so what we just showed is that the integral from a to b is the negative of the integral from b to a. All right. And so essentially what that's saying, and in some sense it makes sense geometrically too. So if we go a to b, and let's actually just draw some rectangles here. So if I'm thinking about going from a to b in some sort of direction like this, and I want to find the area of these rectangles, then I'm going to say, okay, well, the width of this, actually, let's make these specific numbers just to make this really clear. And so I'm saying, okay, well, I moved one to the right, so this is a width of 1. Well, I moved one to the right, so this is a width of 1. And then we could just say that this is the function y equals x. And so this is going to be 1, and then this will be 2, right? And so the area of this rectangle would be 1 times 1. Area of this rectangle would be 1 times 2. All right. But then what if we instead wanted to do the same thing, but we wanted to think about starting at 3 and moving towards 1? Well, then we could almost think of the area of the base of this rectangle as being -1. Because we moved -1 in order to get that base. And so then we could say that the area of this rectangle is -1 times 1, and the area of this rectangle is -1 times 2. Right? And so it's just sort of about the direction that we're moving there. But geometrically, often we just like to think about these positive areas, at least as long as they're above the x-axis. So once again, let's just do one more example. And let's say the integral from 2 to -2 of 4 plus the square root of 4 minus x squared dx. The first thing we want to do is we want to look at these bounds, and we're saying, well, we're going from +2 to -2. So let's switch this so that we're just going from left to right, and then we can think about these areas as usual. So we're going to say that that equals negative of the integral -2 to 2 of 4 plus the square root of 4 minus x squared dx. And then that equals negative, and we're just going to break up this integral. We don't want to forget those parentheses. So for this first part here, it's just the integral from -2 to 2 of the constant function 4. So that is just a rectangle like this. It has a base of 4. It has a height of 4. And so the area is 4 times 4, which is 16. And then for this one, that is a semicircle of radius 2, and we're integrating from -2 to 2. And so remember, the area of a circle is pi r squared, so we have pi times 2 squared, but it's only half of a circle, so it's 1/2 of that. So it's 1/2 times 4 pi, which is 2 pi. So we have -16 plus 2 pi, which we could rewrite as a -16 minus 2 pi. Now, the real power of the net change theorem comes from questions like this. What if we said, what is the integral from 0 to 3 of 3x squared dx? Okay, well, let's try to draw this. So we have some parabola, and we have 0 here, we have 3 here, and we're trying to find this area here. Well, this is not a shape that we really know, right? This is just some sort of triangular looking thing, but we have this one curved side. And so that looks a little bit scary. Maybe we're thinking, oh, maybe the answer involves pi or something, so we have this curved side. But now we have this really powerful tool, and that tells us that this right here, all we have to do is we have to take the antiderivative and we have to evaluate it at 3 and 0, right? So that's going to be our big F of 3 minus big F of 0. And we know what our big F is using our reverse power rule. We know that the antiderivative of 3x squared is x cubed. And the notation that we use for evaluating things at two numbers is this right here. We put it in square brackets, and then I put a 0 subscript and a 3 superscript. Occasionally, you will see other notations. Some people will use a notation like this. They put their antiderivative, and they draw a vertical line, and they use the same subscript and superscript. But I prefer to keep it enclosed on both sides, but the notation you use is ultimately up to you. So that equals, by definition, 3 cubed minus 0 cubed. And so that's going to be 27 minus 0. And now when we think about it, this is a pretty incredible result. We have this novelly shaped area, but we're able to say concretely that that area is 27. And it's also somewhat curious that it's an integer, even with this rounded side. Let's try one more example. Let's say the integral from -1 to 1 of 1 divided by x squared plus 1 dx. So if we were to graph that, it's going to look something like this. Kind of looks like a bell curve, but not quite. And we're interested in this area here. And so what's the antiderivative of x squared plus 1? Well, we know that that is arctangent of x. So we're first going to plug in 1. We're going to say, what is arctangent of 1? Well, what angle gives us a tangent of 1? And that is pi over 4. And then we're going to say, what is arctan of -1? So what angle gives us a tangent of -1? That is within our range of arctangent, and that is going to be negative pi over 4. And so ultimately, this is pi over 4 plus pi over 4, which is 2 pi over 4, which is pi over 2. So that is going to be our answer. Right, and that's this area here. So now let's do something a little bit different. And we're going to say, let g of x equal the integral from a to x of little f of v dv. Now, this is where this idea of dummy variables becomes important. So we're using a v in here, but the choice of letter doesn't matter. And the reason I can't use x is because I'm already using x as my upper limit here. And so when I plug an x into g, that's where I'm putting the x. I don't want to put it inside of this integral. That doesn't really make sense. But since the choice of letter doesn't matter, I'm just going to take my antiderivative of little f, which is my big F of v, and I'm evaluating that from a to x. And so that's going to give me big F of x minus big F of a. All right. Now let's take the derivative with respect to x of g of x, and we'll see that that's the derivative with respect to x of big F of x minus big F of a. Well, we said that big F is the antiderivative of little f, so that means little f is the derivative of big F of x. And now big F of a is just some number, right? I'm plugging a into big F, and I don't know what it's going to be, but it's going to be some number, right? It's not like this first part where it's a function of a variable. A is just some constant, and so I'm taking the derivative of some constant, and so that's just going to be 0. And so that's going to give me little f of x. Okay, and so this is a very important fact, and this is the first part of the fundamental theorem of calculus. And so if we just look at exactly how the textbook phrases this, they say that if g of x is the integral from a to x of f of t dt, they use t's instead of v's, then g prime of x equals f of x. And then the second part, like we saw before, is that the integral from a to b of f of x dx is big F of b minus big F of a, where f is any antiderivative of f. And they separately write the net change theorem, which we see is essentially the same as that second part, except instead of little f, they just write big F prime. But those are by definition the same thing. So now let's try a somewhat related question. And now we're going to say that we want to take the derivative with respect to x of the integral from negative x to 0 of little f of v dv. Okay, so just as before, we know that by the net change theorem, we're going to evaluate the antiderivative of little f, which is big F, at the upper bound first, also called the upper limit, and then we're going to subtract that function evaluated at the lower limit. And then we want to take the derivative of this. So let's see. So the derivative of big F of 0 is just the derivative of a constant. And so that's going to be 0. And then we have minus this derivative of big F of minus x. So we're going to have to do chain rule here. And first we're taking the derivative of big F of minus x. We just get little f of minus x. And then we have to multiply that by the derivative of the inside, which is minus 1. So overall, what do we have? Well, we're going to get f of minus x because those negatives canceled out. And so we see that that's a sort of similar to what happened before, except now we have a minus x instead of a positive x. Right before we said that the derivative of the integral from a to x is little f of x. So there's some connection here. And now what if we make this even more complicated? What if we said we want to take the integral from x squared to x to the 6th of little f of x dx? We can't use f and x in here. Little f of u du. We're just using different letters to get you guys used to these dummy variables being whatever they might be. Okay, so this is going to be, we're going to evaluate big F of x at those limits. So big F of x to the 6th minus big F of x squared. And then, of course, we have this derivative out in front. So we're going to evaluate these derivatives. And once again, we have chain rule. So for this first term, the derivative of big F of x to the 6th is little f of x to the 6th times the derivative of the inside. That's going to be times 6x to the 5th minus, and then we have little f of x squared. That's the outside derivative times our inside derivative. So times 2x. And if we wanted to, we could rewrite that a little bit, but I think both of these presentations are acceptable. Now, if we just kind of look at this for a second and notice what happened, we basically see that we plugged these limits into our function, into the function that is in the integral, right, into the integrand, and then we multiplied by the derivatives of those limits. All right, let's try it once with a little bit more of a concrete example. So let's try this. Let's say the integral from cosine of x to sine of x of 3p squared dp. And I want to take, once again, the derivative of this. And so how are we going to find this? Okay, well, 3p squared, I do know how to take the antiderivative of that, right? We're going to use our reverse power rule, and I know that p cubed is the thing that has a derivative of 3p squared. So my antiderivative is p cubed, and I'm going to be plugging in as my limits cosine of x and sine of x. And then I'm just going to copy down that derivative that I have out in front. So we'll deal with that at the end. So we have the derivative of, so first I'm going to plug in that sine of x. So that sine of x gets plugged in for the p. So we end up with sine cubed of x, and then we're subtracting the other one, so that's minus cosine cubed of x. And remember, don't get confused by this notation. It's just notation. Sine cubed of x means this. It means sine of x all cubed, and likewise for cosine cubed of x. Okay, so now we're ready to evaluate the derivative. So the derivative of sine cubed of x, well, our outer function is just something cubed, so we're going to do our power rule. So that's going to be 3 times sine squared of x, and then we have to multiply by our inside derivative, so the derivative of sine, which is cosine of x. And then we're going to go minus, and now over here for cosine, same thing again. Outside we have x cubed function, so we're going to say 3 cosine squared of x, then times the derivative of cosine, which is negative sine, so times negative sine of x. Now we notice that these negatives are going to end up canceling, so we should rewrite this a little bit. Sine squared of x, cosine of x, they're going to say plus 3 cosine squared of x, sine of x. Okay, now what if we had something like this? We're going to take the integral from 1 to 1 over x of arctangent of y dy, and we want to take the derivative of this with respect to x. Okay, so what's this going to be? So what's the antiderivative of arctangent of y? What's a function whose derivative is arctangent of y? Well, we know that the derivative of arctangent of y is 1 over 1 plus y squared, but we don't know a function whose derivative is arctangent of y. Now, could we approximate an antiderivative? Yeah, sure, right? We could do the same thing that we did earlier with these line segments, and we could try to build up a graph that looks like this antiderivative function. So in some sense, the antiderivative does exist, but we just don't know how to write it, or we're not able to think of a function that will give us that derivative at this point anyways. So let's just say, let big F of x be the antiderivative of arctan of x. And maybe it would be helpful if I called these y's, since that's the variable that we have inside of the integral. So we can just work with that for now. So we're taking this big F of y, and we're going to be plugging in our limits, which is 1 and 1 over x. And then we're going to take the derivative of that with respect to x. So d dx of this. Okay, so let's start by plugging in those limits. So it's big F of 1 over x minus big F of 1. Okay, so now we're taking the derivative with respect to x of big F of 1 over x. Well, let's start with the outside function. What's the derivative of big F of x? Well, since big F is the antiderivative of arctan, then the derivative of that outside function is going to be arctan. And we're keeping the same thing on the inside for now. And now we have to multiply by that inside derivative. Now remember that 1 over x is the same as x to the minus 1. So we can pull that minus 1 out in front. So minus 1 times x, and then decrease the power by 1, the negative 2. And now we finish the derivative of that first part. And then we're going to say minus. And whatever this is just some constant, right? We're just plugging some number into a function. And so that's going to give us some number. And so the derivative of some number is 0. And so ultimately, if we simplify this a little bit, I'm going to get negative. And since we have an x to the minus 2, I can put an x squared in the bottom. And I'm going to put my arctan 1 over x on top like this. And so notice that even though we had to invent this function big F, and we didn't know what it was, by the time we were finished with the problem, that big F went away. And so ultimately, it didn't matter that we didn't know what it was. Let's try another one. Let's take the derivative of the integral from cosine of x to sine of x of e to the negative t squared dt. So let's start the same way that we started before. We'll just say let big F, of course this has to be a different big F than we used in the last problem, be the antiderivative of e to the negative t squared. And that's the same thing that we did before, because once again, we don't know what the antiderivative of e to the negative t squared is. And this is one of these functions that you will not be able to come up with the antiderivative because there's no elementary function, which means a function that you can write out of these pieces that we've learned that will actually give you e to the negative t squared as a derivative. So this is the only way we can do this, actually. And so what's this going to be? Well, we're going to take that antiderivative, we're going to evaluate it at our limits. So big F of sine of x minus big F of cosine of x. And we still have a derivative out in front. We're going to take the derivative of the first part, and the derivative of big F is e to the negative t squared. So it's e to the negative, and then where we have this argument being plugged in, which is sine of x, that's going to replace the t. So instead of t squared, it's going to say sine of x squared, or sine squared of x. And now I have to do chain rule. So now times the derivative of sine, which is cosine of x. And then we're going to say minus. And then same thing here. So we're taking the derivative of this big F. And so that gives us e to the negative t squared. And we're plugging that cosine in for our t. And then by doing chain rule, we multiply by the derivative of cosine, which is negative sine. Instead of t, we plug in cosine of x. So we get negative cosine squared of x. Then we do chain rule and multiply by the derivative of cosine, which is negative sine. So times negative sine of x. And then we can simplify this a little bit. I like to put these trig functions out in front. And then we see that we have these negatives that are going to cancel. So we're going to say plus sine x e to the negative cosine squared of x. And there is one other way that I could write this too. It's really just up to preference, but I could say cosine of x over, and remember e to the negative something is 1 over e to the positive something. So I could say that this is cosine of x over e to the sine squared of x. And likewise for the other term here. All right, and let's try one more example. Let's take the derivative with respect to x from the square root of x to 1 of sine of alpha over alpha d alpha. Okay, once again, we don't know a function whose derivative is sine of x over x, so we're not going to be able to find the antiderivative here of sine of alpha over alpha. And so we're going to do the same thing. So we're going to say let big F be the antiderivative of sine of alpha over alpha. So let's use alpha as an argument here. Okay, and so that just means that we're evaluating big F of alpha between alpha equals root x and 1. And we're taking the derivative with respect to x of all that. So we're going to plug in that 1 and that root x. Remember, the top thing gets plugged in first. So it's big F of 1 minus big F of root x. And that's what we're taking the derivative of. Okay, so derivative of big F of 1 Well, once again, big F of 1 is just some number. Derivative of some number is 0. And then we're saying minus derivative of big F of root x. So we know that the derivative of big F is sine of alpha over alpha. And so in this case, we're going to say it's sine of whatever we're plugging in. So that's sine of root x over root x. And then we have to do chain rule and multiply by that inside derivative. And so that inside derivative is the derivative of root x, which we should think of as x to the 1/2. So when I take the derivative, I pull the 1/2 out in front, and then I multiply by x, and then I'm going to reduce the power by 1. So 1/2 minus 1 is a negative 1/2. And I could think about that as being a root x in the denominator. So let's rewrite this a little bit as a negative sine root x over root x times 1/2 times 1 over root x. And now I have 2 root x's in the denominator, so I can multiply those together and get an x. And so this is going to give me negative sine of root x over 2x. Now, at this point, we've established that there's a very strong relationship between antiderivatives and integrals. But we still haven't developed a way to concisely write antiderivatives without writing this whole tedious let big F of x be the antiderivative of little f of x. So it makes sense that we should want a concise way to write antiderivatives, just like we have a concise way to write derivatives. And many people have had the same idea. And because of this close relationship between integrals and antiderivatives, we've decided to use the integral symbol to denote antiderivatives. And we call these indefinite integrals. And we say that the indefinite integral of a function is the general antiderivative of that function. And we write it like this. So an indefinite integral, we just write the integral symbol with no limits, and then we plug our function inside like this. We include the dx, and then we say that that equals whatever the general antiderivative is. So that's some particular antiderivative plus c, so that we have all of the functions on this right side whose derivative give us the integrand on the left side. We could just do a couple more examples, but it's fairly straightforward. So we could say that the indefinite integral of 1 over 1 plus x squared dx equals arctangent of x plus c. Or what if we tried something like this? What if we said, how about 4e to the x plus x to the 4th plus 7 over the square root of 1 minus x squared dx. Okay, well, we're just going to break it up into parts. So what is the antiderivative of 4e dx? Well, that's going to be 4e to the x. Right, you can double check, take the derivative of 4e to the x. If you're still going to have 4e to the x, so that works. Plus, what's the antiderivative of x to the 4th? Well, remember that we're going to raise the power by 1. So we have x to the 5th, and then we're going to divide by that new power. So I can put a 1/5 out in front, and you can double check to make sure that derivative works. And then what about this one? Well, if you ignore the 7, that should look familiar as one of your standard antiderivatives that you should have memorized. So that 7 is just a multiplied constant. We can just pull it out in front. And then we know that 1 over the square root of 1 minus x squared is the derivative of arcsine of x. So the antiderivative of 1 over square root of 1 minus x squared is arcsine of x. And now we finished. And so we just have to put in our constant plus c so that we capture all of the possible functions whose derivative gives us this thing above. And since we now have this specific indefinite prefix in front of integral, we want to give a specific name to the integrals that we had initially that have these numbers on the limits. And so we're going to say that we call integrals with limits definite integrals. Now we're going to switch gears a little bit because we want to talk a lot more about rectangles, actually. But before we do that, we should take a little detour to talk about summations. Sometimes in math, we want to add a bunch of numbers together. So maybe we want to say, what is 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7? And that's a lot of writing, and it would be even more writing if I wanted to add 50 numbers together. Or what if I wanted to say, what is 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared? And there's so many variations I could do to this, right? I could say, what is sine of 1 plus sine of 2 plus sine of 3 plus sine of 4? And I could add up a bunch of these numbers together. We really want to have a concise notation to be able to write these sums. So we're going to say that this is tedious notation. And the notation that we've developed to write these sums is this symbol, which is called the summation symbol. Now, I think it can look a little bit scary, but it really just means summation. It's just about adding numbers together. And once we start looking at it, I think it will seem a lot less scary. So on the bottom, we're going to define what we call an index. And so often we'll use the letter I. It's common also to see N and K being used as indexes or indices. So we could start I at 1. And then on the top, we're going to say what number I is going to go up to. So let's say up to 7. Now the index will always count by whole numbers. So the index needs to be an integer. And then in here, we're going to write something. So let's say we said I squared. And often what we write in there is going to be some function of I. So I is going to take on all of these values between 1 and 7. So let's say first I is 1. And so then we get I squared is 1 squared, which is 1. Okay, so then I is going to be 2. And then we're going to see what we get inside there. And so then I squared is 2 squared, which is 4. And then so forth. So then it's going to be 3. And it's going to be 4. And so we'll have this be 9. And then we'll get 16. And we're going up to 7. So we'll do the same thing for 5 and 6. And then it's going to be 7. And then our I squared is going to be 49. And this sum means that we're going to add all of these together. And so if you were to do that, you would find that you would get 140. And so what that's saying is that the sum from I equals 1 to 7 of I squared equals 140. What if we just said, what is the sum from I equals 1 to 7 of I? Well, then instead of adding 1, 4, 9, 16, now we're just adding 1, 2, 3, 4, all the way up through 7. And so what's that going to give us? Well, once again, you could just type this into a calculator, or you could do it on your paper, and we're going to find that we're going to get 28 for this one. And you see that we could put any more complicated function of I inside of here, and then we would just evaluate it for each I, and then add all of those together. And so that's all that this notation means. So now we're going to come back to what we were looking at before, which is these rectangles under our curves and how we can use them to approximate the integral of a function. Now, the official name for the sum of the area of these rectangles is a Riemann sum. So let's look at an example. And let's say we want to approximate the value of the integral from 1 to 4 of arctangent of x dx using 50 rectangles. So that's a lot of rectangles. And we're not actually going to do the calculation, but we're going to set up the calculation, and we're going to write the sum using our concise sum notation so that we don't have to write 49 plus signs. Okay. So let's start by drawing a sketch of this. So here's our arctan function. we'll label 1 and 4 on our axis. And so we know that there's a distance of 3 between those. And then we're going to try to break this space up into 50 rectangles, and we're not going to draw all of them. We're just going to draw a couple of them. And even these are probably wider than they should be, but just so we can get some sense of what it's going to look like. And how wide is each of these rectangles going to be? So let's think about that. Well, we have a total distance of 3 that we need to cover with rectangles. And we're going to break it into 50 pieces, right? Into 50 rectangles. So that's 3 divided into 50 different widths. So each rectangle is 3/50ths wide. Now, what's going to be the height of each rectangle? Well, the height of each rectangle is going to be whatever the function value is at the starting point of each rectangle, right? So let's actually try drawing some of these a little bit nicer. Once again, these are much wider than they really should be, but this is just for illustration purposes. So first of all, let's think about how many steps we've moved at the beginning of each rectangle. So when we want to calculate the height of the first rectangle, we're just going to plug 1 into our arctan function to get that this height here of our first rectangle is arctan of 1. Now, what about this second rectangle? How tall is that going to be? Well, what is this point right here? Well, that's 1. And how much did I move to the right? Well, we said that each rectangle is 3/50ths wide. So I added 3/50ths. And so the height of this is going to be arctan of 1 plus 3/50ths. What's this point going to be here? Well, that's 1 plus, and I moved 2 steps to the right. So 2 times 3/50ths, right? Because each step is 3/50ths. And then what's the height of this line going to be? And that's our third rectangle. And so that height is going to be arctan of 1 plus 2 times 3/50ths. Okay. So this 3/50ths is showing up a lot because that is the size of our steps, right? And so we notice that the width of each rectangle is also our step size. And so we call that step size delta x, right? Delta x means change in x. We've used this before in other contexts, or at least you guys have in 141. And so what we're saying here is that delta x equals 3/50ths. And then what is our starting value going to be at a particular step? So let's say at step I, we start at, now we know that originally we start at 1. And so that we can say when I is 0, so our 0th step or our first step, but we're going to 0 index here just to make the math a little bit easier. So it's going to be 1 plus, then it's however many steps we've completed times 3/50, right? So if I've moved 5 steps to the right, then my I is 5. And then it's going to be plus I times 3/50, right? And so that's 1 plus I delta x. And so that means that our height is what we get when we plug this value into our function. So our height is going to be arctangent of 1 plus I delta x. And what is our last I value going to be? Really quick, think about this. So if I went all the way to 50, we start at 0. If I went all the way to 50, we would end over here at 4. And that is the right endpoint of our integral, right? That's the upper limit. But notice that we don't actually want to draw a rectangle over here. So we're not starting a rectangle at 4. So we don't want to go all the way up to 50. We only want I to go up to 49 because our last rectangle is going to be right before here inside of this interval. So let's see if we can write a sum that approximates our area. So our area is approximately, and so we're going to start our I at 0, and we're going to end at 49. And then for each I, we want to calculate the area of that rectangle, and we're going to add them all together. So the area of a rectangle is height times length, right? So the height we said is arctan of 1 plus I delta x times delta x, which is our width. And we do want to write this actually with real numbers. So let's just replace our delta x with what it's actually equal to. Arctan of 1 plus I times 3 over 50 times 3 over 50. And if we just rewrite that one more time, so it's the sum from I equals 0 to 49 of arctan of 1 plus 3I over 50 times 3/50ths. Now, the reason that we defined a delta x up here is because we're going to use this idea in our general formula for Riemann sums. And I'm also going to label some other things with general names. So I'll write these in green, so you can see that these are the generalizations. So what if we call this point that we start at A and this point that we go to B, and instead of calling this specifically arctan of x, we'll just call it f of x. Then instead of knowing that this here is 3, we just know that it's the distance between our A and B. So we could write that as B minus A. And then we also want to say that we're just going to use some number n rectangles. All right, now let's update our width. So our width, we said, was this B minus A divided by n. And so that means that, right, delta x is B minus A over n. And that's a formula that you're going to be using. And then at step I, we start at, we said 1 plus I times delta x. But in general, that's going to be whatever our starting point is, plus I times delta x. And we call this point at step I our xi. So we say xi equals A plus I delta x. And so that means that our general formula here is this sum from I equals 0 to n minus 1, right? We didn't want to use the last rectangle there, of f of xi, right? That's whatever point we're at I. So that's our A plus I delta x times delta x. Now notice that this formula that we just wrote corresponds to a picture like this, where between some A and B, we draw all of our rectangles touching the curve on the left side. But what if I wanted to draw a slightly different picture? What if between my A and B, I instead wanted to touch the rectangles to my curve on the right side? Well, then let's think about where we start. Well, that means that the first place we're going to evaluate the height is here. So that's going to be our A plus a delta x, and then we're going to have A plus 2 delta x. And it looks like here we have n equals 4, so A plus 3 delta x and A plus 4 delta x. So notice that before we started with, we actually plugged in A into the function. That was the first thing we plugged in. And the last thing that we had plugged in was A plus 3 delta x. We never actually plugged in 4. And so we can think of A as A plus 0 delta x, which is why our I goes from 0 to n minus 1 for this type of sum. Or for this type of sum where we start at the right side, we're going to start at 1, right? The first thing we plug in, we're adding 1 delta x. And then we go all the way up to n because we do want to plug in the right endpoint there of f of xi. Remember, xi just means A plus I times delta x. So that's our height, f of xi, times our width, which is delta x. And each of these two formulas have names. So this is called a left Riemann sum because we're approximating the height with the left side of the rectangle. And this one, as you might have guessed, is called a right Riemann sum. Now here we've drawn a left Riemann sum and a right Riemann sum for both an increasing and a decreasing function. Notice that the left Riemann sum, all of the rectangles are underneath of the curve, and so they don't fill up the complete area because there's these little triangles that are not accounted for. Contrast that to a decreasing function with the left Riemann sum. Well, then we overhang the area. We fill up the complete area under the curve between A and B, and our rectangles include these triangles that are in excess of the area under the curve. Now, the opposite is true for a right Riemann sum. We see from our picture that when we do a right Riemann sum on an increasing function, then we have an overestimate of the area because we fill up the whole area, and then we have some more. And with a decreasing function and a right Riemann sum, we don't quite fill up the area because there's still a couple little triangles here that are unaccounted for. So we have this chart here, and we're going to say that a left Riemann sum on an increasing function, just like we saw up here, is an underestimate, right? That's this graph right here. So we're going to write underestimate. But for a decreasing function, we saw that that was an overestimate. And the reverse was true for right Riemann sums. So we saw that we had an overestimate on an increasing function and an underestimate on a decreasing function. Right, and just we can verify really quick that this chart corresponds correctly to these pictures that we drew above. Now it's important to notice, though, that if a function is both increasing and decreasing over our interval of interest, then we cannot easily determine whether the Riemann sum is an overestimate or an underestimate. So we see in this picture here, we have some triangles that are unaccounted for. And of course, when I say triangle, right, these aren't perfect triangles, but they're roughly triangles. And then we have some triangles that are hanging over the area under the curve. And so we don't know whether there's more area hanging over or if there's more area unaccounted for. So it's hard to say for sure if this is going to be an overestimate or an underestimate. And so the only times that we can easily say concretely is if the function is only increasing or only decreasing over the entire interval a to b. Now let's look again at these two pictures that we saw before. And now I've added a third picture, and I've drawn the left and the right sides of the rectangles. In our previous two drawings, the choice that we were making was whether we should draw the top of those rectangles to have the function value of the left or the right side of the interval that that rectangle approximates. But there's a natural third option, which is to have the top of the rectangle be at the height of the function in the middle of that interval. So we could draw this rectangle like this, and this rectangle like this, and so on for each of these rectangles. And now notice that for each of these rectangles, the part of the rectangle that overhangs the function is about the same as the amount of the rectangle that is underneath of the function. So intuitively, this feels like a better approximation of the integral. And in general, we will find that it is. And this is called the midpoint rule. And now we want to come up with a formula for this rule. Well, using our notation before, we called this x0, x1, x2, x3, and x4. But now the x value that we're plugging into our function is this point right in the middle of each of these. So that means that this point is the average of x0 and x1. And this point is the average of x1 and x2, etc. And we know how to compute an average. We know that to find the average of two numbers, we add them together and divide by 2. The book's notation is to call this point x1 bar. And then we just increase that subscript as we move across. And so we could say that x1 bar equals x0 plus x1 divided by 2. Or we could say that x2 bar equals x1 plus x2 over 2. And we see the pattern here. And so in general, we say that xi bar is defined as, now notice that this 2 subscript matched this second thing that we're adding there. So we want to put our xi over here, and then the subscript of the first thing is 1 less than the second thing, so that's going to be x sub I minus 1, and then we divide by 2. So that's our general formula for xi bar. But then if we look at what's actually going on, well, what's the area of this rectangle? Well, that is just the height of the rectangle, which is f of x1 bar times the width of the rectangle, which we called delta x. And we follow that same thing through for all of these rectangles. The last one, right, is going to be f of x4 bar times delta x, right? This is the width, this is the height. And so what are we doing? Well, we're counting from 1 to 4. We're plugging x sub I for each I from 1 to 4 into our function and multiplying by delta x. So in our summation notation, which I should mention is also called sigma notation, we're going to say I equals 1, right? We're starting at 1. And for going up to n, we're including n, which is the number of rectangles, right? We have 4 rectangles here, and we include the 4. And then we're saying f of xi bar times delta x. And of course, in order to use this, we have to reference these other definitions that we created for xi bar here and for delta x above. So let's try an example. It says estimate the area under the curve f of x equals 9 minus x squared from 0 to 3 using 3 rectangles and left endpoints. Now, I don't think it's necessary to go back up and use those formulas because those formulas were what we used to encode the process that we developed to estimate this area using rectangles. So if we go and start with that formula, then we're basically just working backwards to this process that we already know how to do. So I think it's better to just start by drawing a picture. So we have a y-intercept of 9. We notice that we have a negative a value, so we have a parabola that opens downward. And if I factored that parabola, notice that gives me 3 minus x times 3 plus x. So I know that I have roots at 3 and minus 3. And so that's just going to help us with our graph. And then we want to use 3 rectangles between 0 and 3. And so how wide is each rectangle going to be? Well, I think in our heads, we probably can already see that it's going to be 3. But let's just do the math really quick. So delta x we said is b minus a over the number, right? Remember that our right thing is our b, our left thing is our a, and n is the number of rectangles that we're using. So that's b minus a over n, which is 3 minus 0 over 3. So that's 1, which I think we already knew, but in other cases it might not be as obvious. So we step 1, we're at 1, we step 1, we're at 2, and then we're using left endpoints, which means that we're doing left Riemann sums. There's different phrasings of this that you might see in problems. So we're drawing a rectangle like that, drawing a rectangle like this, and we're drawing a rectangle like this. Okay, so we know that the width of each of these rectangles is 1, and let's try to find the height. So for our first rectangle, our height is going to be, well, that is going to be f of 0. So that's 9 minus 0 squared, which is 9. Okay, what about the second rectangle? Then our height is going to be f of 1, which is 9 minus 1 squared, which is 8. And for our third rectangle, our height is f of 2, which is 9 minus 2 squared, which is 5. So the total area is going to be the height times the length of the first rectangle. So that's a 9 times 1, plus the area of the second, so 8 times 1, plus the third, 5 times 1. So that's 9 plus 8 plus 5, which is 17 plus 5. So that is going to be 22. And so what are we saying with that? Well, we're saying that the integral from 0 to 3 of 9 minus x squared dx is approximately equal to 22. And because this is a decreasing function over the entire interval 0 to 3, we can also see that this is an overestimate since we're using a left Riemann sum. So we know that our approximation here of 22 is too big, right? So it would also be correct to put a less than sign here. But the point isn't just that this integral is less than that, it's that it's also somewhat close to that. Now let's do the same thing, but instead do a right Riemann sum. You might see that phrased as repeat the above using right endpoints. All right, well, let's redraw our graph. Now this time, we're going to go up from 1, and we're going to stop the rectangle right there. And then we'll do the same for 2 and 3. How tall is our last rectangle going to be? Well, f of 3 is 0, so our last rectangle is really just this degenerate rectangle that has a height of 0. So our total area is going to be the height of this first rectangle, which is right here, which is f of 1. And so let's say f of 1 times the width of 1 plus f of 2 times the width of 1 for our second rectangle plus f of 3 times the width of 1 for our third rectangle. And it's totally fine to just write this out like this. We don't need to go through the whole thing of writing all these words, especially if we were using more rectangles. It's actually pretty reasonable to see problems that have maybe up to 8 or 10 rectangles. So we're just going to write this out like this. And then f of 1 is what? That is 9 minus 1 squared. And multiplying by 1 is just keeping that the same, so I'm going to ignore that. 9 minus 2 squared. And our last one is 9 minus 3 squared, which, as we saw for the picture, is 0. So this is going to give me 8, plus 9 minus 4 is 5. And this last thing is just 0. And so in total, that's going to give me 13. So this time, our estimate is that the integral from 0 to 3 of 9 minus x squared dx is about equal to 13. But now we see that our rectangles are fully underneath of the curve, and there's a lot of space that we didn't fill in. So we know that 13 is too small. So our real area is bigger than 13. And now let's do this one more way, and this time we're going to use the midpoint rule. We've drawn our graph again. Remember, this time we want to plug in these points halfway in the middle of the rectangles. So in that case, that's going to be 0.5, 1.5, and 2.5. So if we plug in 0.5, our rectangle is going to look something like this. 1.5, our rectangle will look like this. And 2.5, our rectangle will look like this. And then we want to find the areas of each of these. So once again, it's the height of the rectangle. So the height of this rectangle, right, is exactly the height of the function when we plug in that 0.5. So it's f of 0.5 times that width, which is 1. And we're going to repeat the same for the other two midpoints. Once again, since we have a width of 1, I'm just going to ignore that 1 here. And so we have 9 minus 0.5 squared plus 9 minus 1.5 squared plus 9 minus 2.5 squared. So we have 9 minus, and that's going to be a quarter, plus 9 minus 2.25 plus 9 minus 6.25. All right, now let's see how much math I can do in my head. So we have 8.75 for this first subtraction, plus 6.75 for the second subtraction, plus 2.75 for this third subtraction. And so I think that's going to give us, let's see, 8 plus 2 plus 6 is 16. And then 75 times 3 is 225, so it should be 18.25. Okay, I just double checked, and that is correct. So what we're saying, once again, is that the integral from 0 to 3 of 9 minus x squared dx is approximately equal to 18 0.25. Now, we know that we can actually calculate the real answer of this because we know the antiderivative of 9 and of x squared. And so we're going to avoid going through that right now, but I'll just tell you the answer is that the actual answer is that the integral from 0 to 3 of 9 minus x squared dx is exactly 18. And so we see that we actually did a pretty good job here with our 18.25. Even just using these big width 1 triangles, we did a pretty good job with this midpoint rule. As we saw before, 13 was too small, our 18 was bigger than 13, and our 22 was too big. So we created this upper bound and lower bound, but they were pretty loose. We had a lot of wiggle room in there. This midpoint rule got us really close though. So the midpoint rule is a really great technique to approximate integrals. And now let's look at just one last type of problem. So our question says, the following is a left Riemann sum for a certain definite integral, which is the integral from 2 to b of f of x dx. Find b and f of x. So we have this sum here, and we're trying to figure out what it is that they're integrating. So we could think about this as, imagine we know that someone solved a problem like these problems that we have up here, and you have a piece of their scrap paper, but you don't have the original problem. And just based on this scrap work that you have, you're trying to kind of reverse engineer what that original problem was. Now we have the left Riemann sum formula over here for you to reference. And we know that what's written right here is what's written right here, right? This is one term in the sum. And the first term happens when I is 0. So that means that this is supposed to be f of x0 times delta x. Okay, now what does delta x mean? Well, delta x means b minus a over n, right? So let's rewrite that. So f of x0 times b minus a over n. Now it's looking like this b minus a over n should line up with our 3 over n. So those are probably the same part of this product here. And so let's just work with that a little bit off to the side. So b minus a over n. So if that equals 3 over n, then we're saying that b minus a equals 3. And we know what a is, right? Because a is the lower bound of the integral, which is 2. So we have b minus 2 equals 3. And so that already gives us that b equals 5. So we've already solved one part of the problem, right? So our b minus a over n is 3 over n. And let's rewrite the x0. Remember that xi is a plus I delta x. So x0 should be our a, which is 2, plus I, which is 0, times delta x, which is 3 over n. And then we're going to multiply that, of course, by our b minus a over n, which is 3 over n. And so now we also have this alignment of these first parts. So we're saying that f of 2 plus 0 times 3 over n equals 3 over 2 plus 0 times 3 over n. And there isn't really any official algebra that we can do here. We just need to look at this. And we're saying if f of 2 plus 0 times 3 over n equals this, well, we notice that this thing right here is the thing that we have in the denominator here. And so we're saying, what function am I plugging that into, right? What is my f that I'm plugging that 2 plus 0 times 3 over n into? Well, if we look at it for a second, I think we can see that f of x equals 3 over x, right? And just look at that. So whatever we had in the function became the denominator of a fraction whose numerator is 3. And that's true. And if we just go back up to our sum here, we can verify that this works for each of the terms. We notice that as our I increases, we multiply our delta x by something one more. Right here, we multiplied by 1. Here, we multiplied 3 over n by 2, right? That's 2 times 3 over n. And we go all the way up to n minus 1, which is our upper limit here. And so the last term we multiply n minus 1 times, and that was supposed to say 3 over n, right? And so that all works out. And so this is our answer, that f of x is 3 over x. And that's all we're going to do today, and I'll see you in our next lecture on U substitution.